Hi, period 3, Algebra 2 Honors. This is Ms. Skokin, and we're going to finish our notes in section 2.7. So you'll see that this is where we left off. We were working on the example, and let's see, this is example number 2, and we want to solve quadratic inequalities using tables and graphs. So we have two different inequalities. The first one, x squared plus 8x plus 20 is greater than or equal to 5. What we did is we went in our calculator, our graphing calculator, and we graphed as two separate functions, the left-hand side of the inequality and the right-hand side of the inequality. That gave us a parabola for the x squared plus 8x plus 20 part, and it gave us a horizontal line where y is equal to 5 for the second part. What we're going to do then is take a look at where the values of x are, or I'm sorry, which values of x actually give us a value of the parabola which is larger or equal to our 5 number, okay? So we found two values, -5 and -3, that are larger than our horizontal line. So we know that this horizontal line is y is equal to 5, and the other part is the parabola, the x squared plus 8x plus 20. So all of this area up above y equals 5 is greater than, and we decided that the values that are important or critical to answering this question are -5 and -3. We also said that the graphing, if we're graphing the solution set on a number line, is going to be on the outside. So it's going to be joined up with an OR. So when we write that up on our solution set, we're going to say all values of x such that x is less than -5 or, it's less than or equal to, isn't it? Less than or equal to -5, or x is greater than or equal to -3. And that represents the graph that we just created. Let's take a look at the next one. And this is where we're going to, again, look at the inequality and the relationship between the left-hand side and the right-hand side. On the left-hand side, we have this same thing that we had a little while ago, the x squared plus 8x plus 20, giving us the parabola. So here's the parabola that we ended up with. And then on the right-hand side, we again have this y equals 5 line. Okay, so this time what we're looking for is values that are less than 5. So values of the parabola that are less than 5, and I'm just going to highlight that in yellow so we can see it. Any number below the y equals 5 line is going to be less than. So we're talking about all of these numbers here. Now notice that this time our inequality is a less than, but it doesn't have the or equal to. So instead of having solid, we're going to have open circles right here. And what that means is when we graph this on our number line, we're going to have, and recognize that because these are the same parabola, the left-hand side and the right-hand side, we're still at -5 and -3. So we're going to have -5 and -3. But just like we learned before, when the shading is between, see, we're going to have open circles. When the shading is between, the solution set also shows it being in between. And so what that means is we're going to write this as all values of x such that x is between -5 and -3, not including either one of those numbers. Okay? Now, if we look at it on the table, we can see that when it's equal to 5, that's kind of our turning point right here. So when we're greater than 5, it's going to be starting there, and let's see, where's our other 5? Right there. Did I do that right? No, that doesn't look right at all. Okay, so let's see, our 5 is, there we go, that's better. All right, so the numbers in between -5 and -3, we can see these are going to be the ones in yellow, and these are going to be the ones in green. Okay, so So we used a table, as you can see, where I marked it as yellow or green, and we also used the graph. Either way you can do it, but this is a graphical way of solving a quadratic equation in one variable. And let's see, I want to make sure we put our solution set. We did put our solution set up there. Okay, so we found the specific points that helped us to determine the solution sets. These points are known as critical values. And we actually might call them, they're critical values because of where they hit, but if we had moved the 5 over to the other side of the inequality and then use the quadratic formula, for example, we would have called them zeros. They weren't zeros because the 5 was on the other side and we left it there. So the thing that we would need to do is find the critical values first if we want to solve a quadratic inequality algebraically. Critical values we know we can find using either factoring or completing the square. Quadratic formula. I don't know if there's anything else. If there's anything else, you can write it down. Okay? So let's take a look then at the next page. We have an example, and in example 3, it says we want to solve a quadratic inequality algebraically. And what we need to do, we're going to graph the solution set. Of course, that's going to be on a number line. And how do we know that? We know that because there's no y in our inequality. The only variable is x. So we're going to solve the related equation by factoring, completing the square, or using the quadratic formula. The solution is, or are, going to be the critical values. And then let's do that first of all. So pause the video, and this is going to be factorable, so go ahead and factor it, and then we'll proceed with step number 2. Okay, so we have finished step number 1. We moved the 3 over to the negative 3 over to the other side. We saw that it was factorable. We factored, and we found the critical values. The next thing that we're going to do is split up the number line into 3 different regions, and the critical values are going to help us divide up the number line. Okay, so you can see the number line that I've drawn, and we have it divided into basically 3 sections or 3 regions. And the critical values define the 3 regions. So what we're going to do next is pick some test values. And we're going to use a test value in each of the 3 regions. So a nice easy number on the left of 3 would be 0. And between 3 and 7, we also want to pick a nice easy number. So let's pick maybe 5. And then on the right-hand side of 7, we have another region, and we'll use a number like 8. So what I want you to do now is pause the video. Using the original inequality, plug in for x the different test values that we've come up with, and then see where you find a true inequality. You're going to use the original inequality. And turn the video back on when you're ready to check your test value results. Okay, so now that you've turned the video back on, you can see that the area where we have a true, the region that we have a true, is the area between 3 and 7. We look at the inequality, and the inequality does not have the or equal to. So what we're going to do is have open circles on our number line. We're going to graph between 3 and 7, and then the last thing that we need to do is write the solution set. And the solution set, if you remember, goes along with, so this is going to be all values of x such that x is between 3 and 7, exclusive, meaning 3 and 7 are not included in this. And that brings us to example number 4. Number 4 says the monthly profit P of a small business that sells bicycle helmets can be modeled by a function P of x is equal to negative 8x squared plus 600x minus 4200, where x is the average selling price of a helmet. What range of selling prices, meaning what values of x, will generate a monthly profit, meaning P of x, of at least 6,000. So the different things that we need to do here are set up our variables, set up our inequality, and then solve the inequality by solving first the related equation and then using test values. So I'm going to ask you to pause the video now and try to at least set up your variables and your inequality, and then turn the video back on. All right, so we've got our variables defined, we've got the question that we're trying to answer defined, and then we've got our inequality defined. The next thing that we need to do is solve the inequality, or actually solve the related equation. And what that means is we're going to replace that inequality symbol with an equal sign, and then we're going to solve the way we normally would, which means that that 6,000 is going to go over to the left-hand side so that we can set it equal to 0, and then we can use the quadratic formula to solve this inequality, or actually solve the related equation. As always, we're going to end up with two values. Now, what you need to make sure of is, in this case, you're going to need to use a test value and make sure it still satisfies whatever your test value is, so you can figure out where on the number line your region is that constitutes your solution set. So finish this problem up, and when you turn the video back on, you'll see the answer. Let's see, I think that that's it for this section, and we'll resume in section 2.9. Okay, so we ended up with two different values, $26.05 and $48.96, as a result of using the quadratic formula. So we know we can test a value on the outside of the region between 2605 and 4896. So basically we have three different regions once again on our number line. And the values on the left, we could test 20, we could test 50. What I chose to do is test 30, which is between the two. And we plug that into our original inequality that we started with. I ended up with a statement that's true. 6,600 is greater than or equal to 6,000. That's a true statement. So what that means is helmets that are priced between $26.05 and $48.96 will generate a monthly profit of at least $6,000. And that is the end of section 2.7.